Part A just wants the electron configurations of a nickel atom and then a nickel 2 plus ion. So looking at your periodic table, you can see nickel is there in the D block, and so we've got 1s2, 2s2, 2p6, 3s2, 3p6, the usual stuff that all these fourth row elements will have as you read through. And then looking where nickel comes, you can see it's the 8th one across within the D block. It's not one of the weird ones. Remember, copper and chromium don't fit the normal pattern, but it's not one of those. So if it's the 8th one across, that means it's going to be 3d8, and then remember it has 4s2 as well. If you write those two the other way around, 4s2, 3d8, that would be okay, but that's the way it's normally written. So that's the nickel atom. Now if it's nickel 2 plus, what you have to remember is that when transition elements form simple ions, they always lose 4s first, and only then do they start losing 3d. So if it's just 2 plus, all it's going to lose are those two 4s electrons, and the 3d8 will remain intact. So nickel 2 plus is the same as that, except it doesn't have the 4s2. So we just get this, and that's the answer. Okay, part B wants a diagram of a cell that will let us measure the standard cell potential for that reaction. So obviously we've got two half reactions there. We've got nickel going to nickel 2 plus 2 electrons, so that is going to be happening in one of the half cells, because remember each half reaction happens in one of the pots, one of the half cells. So that's one of them, and the other one then is that we have I2 aqueous gaining 2 electrons to give you 2I minus in the other one. So we just separate the two half reactions physically by putting them in separate pots. So one of them, we need our pot here, we've got solid nickel involved, so we make the electrode out of that. So there is our, let's draw it like this, doesn't really matter how you draw it, but just draw it like this. So we'll put a nickel electrode in there, connected up to our circuit, and the nickel 2 plus ions need to go in the solution that it's dipping in. So we put Ni2 plus aqueous. So put the state symbol in to make sure it's clear that it's an aqueous solution there. So that's one of the pots, and then that's connected via a wire with a voltmeter on it and a salt bridge, which you draw like that, and you must label that salt bridge because that's not a standard symbol. So you've got that in there, and that's going to dip into the second pot. And this one has to have the aqueous iodine and the aqueous I minus. So neither of them is a chunk of metal, and that means that this time the electrode has to be made out of platinum. And then again you have the solution, and both of these substances, the iodine and the I minus, have to be mixed up together in that solution. So we have I2 aqueous and I minus aqueous all mixed up there. So that's the setup, and if we measure the voltmeter reading there, that will give us a cell potential, but it specifies standard cell potential, so that means we've got to specify the standard conditions, which means that we want 25 degrees C. You can put down 1 atmosphere pressure, although there's no gas involved, so that's not really a kind of critical condition. But what is critical is the concentrations of the things in solution. So the nickel 2 plus and the iodine and the I minus all want to be 1 mole per dm cubed for standard conditions. And that will give you your marks. Next it wants to know the value that we should get for the standard cell potential, and you can get that from the two electrode potentials which are given in the table at the top. So these are the two values, and it's just the difference between them. So we get that the standard cell potential, E0 cell, is the difference between the two, so that's plus 0.54 minus 0.25, which is 0.79 volts. Okay, so it's just about being careful with the signs here. So you've got to subtract the 2, so it's 0.54 minus 0.25, which you can either enter into your calculator like that or recognise that minus is the same as plus, and that's the value that you get. If you did it the other way around, if you did minus 0.25 minus 0.54, you'd get minus 0.79, but remember that the cell potential doesn't have a sign, and so you would just ignore the minus and get the same answer. So now we've got to write the overall equation for oxidation of Fe2 plus by acidified hydrogen peroxide. So these are the two relevant half equations taken from your table, and the point is that if Fe2 plus is being oxidized, this one's got to go that way. Fe2 plus losing an electron is oxidation, and therefore this one has to go in the reduction direction, which is forward, so the H2O2 is being reduced, and you can just double check if you want that this one has the more positive potential, so it will indeed go in the reduction direction. So we've just got to combine those two half equations, and that means that because this one's going backwards, we've got to rewrite it in the normal way with now Fe2 plus on the left, so that it will go forwards to Fe3 plus an electron. And then we've got to do a bit of multiplying so that when we add the two equations together, the two half equations together, the electrons will cancel, and you see they don't at the moment. But if we simply double this, so double every every term in that, then now we have 2 electrons on the right here, 2 electrons on the left there. So when we add those two together, we get the correct combined equation, which is H2O2 plus 2H plus 2Fe3 plus goes to 2Fe2 plus, that should be on the left, goes to 2H2O plus 2Fe3 plus is the answer. Whenever you do that kind of business combining half equations, once you've done it, check two things. First of all, does anything need cancelling? If it's there on both sides in the equation, but you can see in this case there isn't anything on both sides, so there's nothing to do there. And then just do a quick check, make sure the charge is balanced, because that will usually pick it up if you've made a mistake. So we've got 2 2's are 4 plus 2 is 6 plus on the left, and 2 3's 6 plus on the right, so that looks fine. Part 2 wants us to explain how acidified dichromate can be reduced to chromium 2 plus by zinc in 2 steps. So we've got to find the relevant half equations from the table at the top, and here they are. So here's the zinc one. So zinc is being, zinc would have to go this way and be oxidized to zinc 2 plus to enable the dichromate to be reduced. And you can see the 2 steps, because the one that you're given that actually involves dichromate just takes it down to chromium 3 plus. So then you're going to have the second stage, which is 3 plus to 2 plus. So what we have to do is, first of all, to explain why those are feasible reactions using the electrode potentials that we're given, and also construct the equations by combining the half equations. So if we look at the first stage, we've got to combine these two, and the key thing is that you can see that this one is much more positive, plus 1.33 volts for the dichromate one, and minus 0.76 volts for the zinc one. So the key word in all these kind of questions involving electrode potentials is that which reminds you that reduction and positive go together. And so that's the key idea, that because this electrode potential is more positive, that means that reduction is the feasible direction here, and that's the forward reaction. Dichromate gaining electrons being reduced to chromium 3 plus is feasible, and therefore the zinc will go in the oxidation directions. So that's what we need to explain. So we can write something like this, that E0 is more positive. Absolutely essential that you write in terms of more positive, more negative, whatever, but not bigger, smaller. That is very ambiguous, and they won't accept it when you're talking about things that can be positive or negative. So always go for more positive, less positive, whatever. So E0 is more positive for And then when you're referring to the particular half reaction, you shouldn't really do what we do in casual conversation, which is say, oh, for the dichromate one, because that's not clear. You've got to specify the reduced and oxidized form. So either you have to write the whole thing out, which would obviously be incredibly tedious, or you just write this kind of thing for dichromate Cr3+. Okay, and that shorthand is acceptable then, because that makes it clear which half reaction you're talking about. So it's more positive for dichromate Cr3+ than for zinc 2+, and that's enough of an explanation so that you can then say, so reduction of Cr2072- to Cr3+ is feasible. And that's what it means when it talks about the equilibria, which is the feasible direction, is really what it means when it's talking about the equilibria. So that's the explanation. Now we've got to put them into an actual equation. So you can see the dichromate one is going in the right direction. The dichromate is going to be reduced. So we've got this one going forward. So Cr2072- plus 14H plus 6 electrons go this way to 2 Cr3+ and 7 waters. But the zinc one is going to go that way, so we need to write it the other way round, with zinc on the left hand side going to zinc 2+. But the other thing is that we've got to make the electrons balance, because this has got 6 electrons in it, this one needs to have 6 electrons in it too, so that when we add them together the electrons will cancel. So that means that instead of just having one zinc there, which liberates 2 electrons, we need 3 zincs, giving 3 zinc 2+, because that will then give up 6 electrons, which will feed into the dichromate reaction. So now we can add those two together. So Cr2072- plus 14H plus 3Zn is our combined left hand side, leaving out the electrons because we know they're going to cancel, gives you 2 Cr3+ plus 7 waters plus 3 Zn2+. And that should be the right equation for the first step. Always before you move on though, do 2 checks. First of all, check to see if anything needs cancelling. If you ever have an equation with the same thing on 2 sides, you're going to lose a mark for that. But there is nothing here like that, so that's fine, there's nothing to be done. And then finally, just a quick check is always worth doing, is to make sure that the charges add up to the same thing on both sides, because that will usually pick up little slips you may have made. So 14 plus and 2 minus is 12 plus on the left, 2 3s are 6, 3 2s are 6, 2 6s are 12, so 12 plus on the right as well. So that looks fine. Okay, so that's it for the first part of the reduction, going to chromium 3 plus. So now for the second bit, having made Cr3 plus by reduction of dichromate, we have to realise that reduction of Cr3 plus to Cr2 plus is also possible, because although these numbers are both negative, this is the less negative one, and therefore reduction is the favoured direction for this one. So it won't stay at chromium 3 plus, the zinc will reduce the Cr3 plus further to Cr2 plus, because reduction is the favoured direction for that one as well. So we just go through the same kind of thing, and we explain that E0 is more positive for Cr3 plus Cr2 plus than for Zn2 plus Zn. And so reduction of Cr3 plus to Cr2 plus is favourable. Okay, so again it's the wrap thing, that because this is the more positive or less negative one, however you want to put it, reduction is the favourable direction for that one. So you explain that. And then again you just need to put that in equation form. So once again, because this is going in the oxidation direction, we need to write it backwards. So we've got zinc going to zinc 2 plus, having lost electrons as it was oxidized, and this one going in the forward direction. So we get Cr3 plus going to Cr2 plus, plus an electron going to Cr2 plus. So those are our two half equations. So it's easier this time because all we have to do is just double this one. And then we have 2 electrons on each side. So we just get zinc plus 2 Cr3 plus goes to zinc 2 plus 2 Cr2 plus. And that should be right, but again just do the checks, nothing to cancel. 6 plus on that side, 2 plus and 4 plus, 6 plus on that side. So that looks fine. Okay, part D depends heavily on having learnt your inorganic chemistry, because this isn't really about figuring stuff out except for the amount of water crystallization in the last bit. Other than that, it's about knowing your reactions. So if you've been tempted to try and get away with not bothering to learn them, this is the evidence that says, well, you've really got to do that, because there were a lot of marks up for grabs here. So the first one is aqueous copper 2 plus reacting with excess ammonia to form a deep blue solution. So you absolutely have to have learnt this reaction. So aqueous copper 2 plus, first thing to remember is that you've got to write out the actual formula of the complex ion, which is that. Because this is a ligand substitution reaction, and in ligand substitutions you can't get away with just Cu2 plus aqueous. You can do that if it's like a redox reaction, which we'll come on to in a minute, but not in a ligand substitution. So you've got to have that. And what you have to remember is that there are 4 ammonias substituting, not all 6, and that's just one of those things you have to know. It's a ligand substitution, so it's a reversible reaction, and what it gives you is this complex, that you get copper with 4 ammonias, but still 2 waters as well. And that's still 2 plus because all these ligands are still neutral, so there's no change in the overall charge. And you've displaced 4 of the waters, so you get 4H2O as well. So that's the formula of the complex, that's the ligand substitution equation. But because it specifies that C is a trans isomer, you've got to actually draw it out, because that formula is ambiguous. That could be the cis one, but it is actually the trans one that's formed, so you've got to draw it. So that means that you draw your octahedron. So you put the copper in the middle, and remember the way you draw an octahedron is like this. You've got to put the wedges and dashes in. You won't get marks if you just draw it as if it were flat. So you've got to have that sort of shape for an octahedron. And then if it's trans, that means the 2 waters are 180 degrees apart. So for example, you could draw them like that. Make sure that the oxygens of the waters are on the ends of the bonds, because those are the ones that donate the electron pairs to form the coordinate bonds. And the 4 ammonias go around the middle, and again it's got to be the nitrogens on the ends of the bonds. So this gets drawn like that. And finally, because it's 2 plus, the whole thing gets a bracket round it, and the 2 plus goes outside. So that's the structure of the ion which you need to draw. Okay, reaction 2 is again one of these standard reactions which is there in the notes, which we say you really should learn, which is that copper 1 oxide is a stable compound, but as soon as the copper 1 ions get into solution, they disproportionate. So we can write the equation for that. So copper 1 oxide, first of all, make sure you get the formula right. So copper 1 means that you have 1 plus ions. Oxide, you know, is 2 minus. So the formula for copper 1 oxide is Cu2O to make the charges balance. So we can write the equation Cu2O, which is a solid. And you could write the full equation with sulfuric acid, but it's easier actually just to write the ionic equation. So we can just put 2H plus in there, because you know it's oxide plus acid forms water plus normally the salt, so we need 2H plus to balance with the oxygen to make the water, and so that gives us H2O. And normally, as I say, the pattern is oxide plus acid goes to salt plus water, so what we would have expected to get would be those two copper 1 ions now going into solution. But that's not what you get, because aqueous copper plus is not stable, and so what you get instead is that those two copper 1 plus ions disproportionate, meaning that one of them oxidizes to copper 2 plus and the other reduces to copper metal. So rather than that, we get plus Cu2 plus aqueous plus Cu solid. So that's the reaction, but you have to really spell out how this relates to all the things it says in the question. So first of all, you have to explain that aqueous copper 2 plus contains the complex ion, which is CuH2O6 2 plus, which is blue. Okay, so you have to know that colour, that hexaqua copper 2 plus is blue, and so that accounts for solution D. And this is the brown solid. So this is E. And the other thing is we need to really spell out why this is disproportionation. So you explain that the oxidation states so Cu is plus 1 in Cu2O, and that's converted to plus 2 in aqueous copper 2 plus, which means it's been oxidized because the oxidation state got more positive, and it went to 0 in solid copper, meaning that it got reduced. Okay, so that's spelling out why it's disproportionation, that the same element was both oxidized and reduced in the same reaction. And you should say that, just trot out the definition of disproportionation. So put the numbers down and say, therefore, the copper was both oxidized and reduced in the same reaction, so it's disproportionation. You just have to spell things out to make sure you've explained all the things in the question. It would be easy to basically get that right, but perhaps not put in enough of that detail to get all of the marks. So just try and pay attention, make sure you answer as thoroughly as you can to explain all the things it says in the question. Reaction 3 then is just the standard oxide plus acid goes to salt plus water question. So that the reaction that takes place, copper 2 oxide, is just CuO, because you've got the 2 plus on the copper to balance the 2 minus there, so that's a solid. Reacts with 2 moles of nitric acid to give you copper nitrate, which is CuNO3 2, and that will be aqueous plus H2O. Okay, so that's the reaction that takes place between the copper oxide and the nitric acid, and if you filter off the excess solid copper oxide, as it says, what you get then is that aqueous solution. And if you evaporate some of the water off, you're going to crystallize that out, but the crucial thing is that it forms a hydrated salt F. So in other words, what we're going to get is F, which is copper nitrate with some unknown amount of water of crystallization in it. So the only bit we have to actually figure out from the calculation is the value of X. So it gives us the percentage masses, so we just plug the numbers into the normal empirical formula method. So draw the little table out, write down the percentage masses, divide each of them by the AR to turn them into the relative moles. Okay, so you divide copper by 63.5 and hydrogen by 1 and so on. That gives you the relative moles, but we want them in whole numbers, so we divide through by the smallest of them, which is this one, and you get these numbers. So based on that, what we get then is that the empirical formula is Cu N2H6O9. However, we know that that's actually copper nitrate with some waters, so we know that those two nitrogens are from the two nitrate ions, so that fits. And we also know that 6 of those 9 oxygens come from the nitrates as well. So what that leaves is 6 hydrogens and 3 extra oxygens, so in other words 3 waters. So it's very easy to get from that that's equivalent to Cu NO32. We knew from the chemistry that it would be that, and just looking at the atoms that are left over, we get 3 H2O, and that's what F is.